So up till now, we've really only done examples of integration by parts with the indefinite integral. So I wanted to show you an example where if you needed to incorporate a definite integral in the process of integration by parts, we'd know what to do. Now, in the textbook and in most places that you look, you'll see this following formula for integration by parts using the definite integral. So if you know you've got something that requires integration by parts, yet you have two bounds that you need to evaluate it at, you essentially just apply those bounds to each of the components of the integration by parts formula. Now, I'm going to go ahead and start a problem here using this formula, but I'm going to also direct your attention to what I think might be a quicker way to deal with this. And I'll leave it up to you in terms of how you approach it, but keep in mind that we might have a more direct way to getting to this if you're interested. So this particular example is asking us to find the area of the region bound by the curve y equals 2x times e to the power of 6x, and the x-axis over the interval from 0 to 3. So we know that this area, since we're talking about finding area of a curve, it's going to be between the curve. I mean, this is always going to be a positive curve on this interval, so it'll be just that area, and then the x-axis is the other boundary. So it's going to end up being the integral from our bounds 0 to 3 of 2x e to the 6x dx. And there are a few ways that we could approach this. If we wanted to pull the 2 out, that's fine. But this is the way that I'm going to set it up for this one. So we're going to do our integration by parts, and I'm going to choose as our dv the exponential function, which in this case is e to the power of 6x dx, which leaves us 2x for our u. We differentiate to get du, which is going to be 2dx. We integrate to get our v, which is going to give us 1/6 e to the 6x. And now we apply this. So if we used this formula above here, incorporating the bounds right away, this is what this would end up looking like. So our area would be, so u times v, which would be 2x times 1/6 e to the 6x, evaluated from 0 to 3. So that's this part right here, the u times v from a to b. And then we subtract the integral from 0 to 3 of v du, which would be 1/6 e to the 6x times 2 dx. All right, so I think we can do some significant cleanup here before we move on. So I'm going to go ahead and multiply out these coefficients here, and that's going to give us, what, 1/3. I'll pull that out front, and then we've got x e to the 6x, which we evaluate from 0 to 3. And then if we multiply the 2 and the 1/6 here, we can pull out 1/3 again, and that would be times the integral from 0 to 3 of e to the 6x dx. Okay, so now if we integrate that next integral, this one won't be too bad for us. So we've got 1/3 x e to the 6x 0 to 3. We're going to wait to evaluate until we're all done here. Minus 1/3. And if we integrate e to the 6x, we've done this a few times, we know that this is going to end up being 1/6 e to the 6x evaluated from 0 to 3. And one last step here for cleanup before we move on to actually evaluating this. So we've got our front part right there from 0 to 3, so that really hasn't changed. I'm going to pull that 6 out, that 1/6, excuse me, as 1/18 times e to the 6x evaluated from 0 to 3. Now there's absolutely nothing wrong with now evaluating these two pieces from 0 to 3. However, since the bounds are the same in both of these cases, we can actually just bring them together and say that this is going to be, we could say that this is 1/3 x e to the 6x minus 1 over 18 e to the 6x evaluated from 0 to 3. So it's really up to you. If you prefer this case, because that might be a little bit easier, or we could do the first one here. I'm going to go ahead and follow through with this first one since we've started with that. But I just wanted to point out that you've got a couple of options here. So if we go ahead and plug in our bounds, we're going to have 1/3, and then if we plug in 3, we'll have 3 times e to the power of 6 times 3 minus 0 times e to the power of 6 times 0. And then we'll have minus 1 over 18 times e to the power of 6 times 3 minus e to the power of 6 times 0. So just to be clear of what we're doing here, this part of our problem came down to this, and this part of our problem develops right here. And now we just go ahead and we multiply this out and clean it up and see what we end up with. It's not going to be a particularly nice answer, but we'll just kind of do our best. So luckily the zeros help out. So we're going to have 1/3 times 3e to the power of 18 minus 0 in this case because we're multiplying by 0 there. Now we've got minus 1 over 18 times e to the 18, and be careful for this, we've got minus e to the 0, which is going to be minus 1, because e to the power of 0 is equal to 1. And now it's kind of a matter of cleaning this up until we don't feel like cleaning it up anymore. Let's see what we can do. So we'd have 1/3 times 3, that's going to give us e to the 18. If we distribute that negative 1/18, we'd have minus 1/18 e to the 18 plus 1 over 18 if we distributed that through. If we got a common denominator of 18, what would that give us? 18 e to the 18 over 18 minus 1 e to the 18 over 18, sorry, lots of 18s here, plus 1 over 18. So that's just getting common denominators. And we could combine that, and that would give us, 17e to the power of 18 plus 1 over 18, which is approximately 62,012,193.13 if we wanted to approximate it, but this is a perfectly tidy little exact answer right there. So in the end, incorporating the definite integral with integration by parts is not too different from just the definite integral in general. We're integrating, and then we apply the bounds once we're done. And I think that's probably the best way to think about it, is not get too worked up about what the formula looks like, and just remember, okay, I'll do my integration by parts, and at the very end, when I'm all done integrating, I'll evaluate that result from my two bounds.